There's something profoundly humbling about staring into the depths of space, realizing that what we see is just a whisper of the universe's vast, untold story. And if there's one place where that story takes a turn into the downright mysterious, it's the Perseus Cluster. Imagine a structure so colossal it contains thousands of galaxies, each with billions of stars, all bound together by gravity in a cosmic dance. This isn't just another patch of the universe, it's one of the most massive objects we've ever discovered, a titan lurking in the constellation Perseus, over 240 million light-years away. But here's the thing, the more we learn about it, the more questions we uncover. Because nestled within this gargantuan cluster are phenomena that defy explanation, whispers of something stranger, something darker, something science is still struggling to understand. Think about that for a moment. In an age where we've mapped the human genome, sent probes beyond our solar system, and peered back to the dawn of time itself, there are still corners of the cosmos that leave even the brightest minds scratching their heads. The Perseus Cluster isn't just a destination for astronomers, it's a riddle wrapped in enigmas, a place where the laws of physics seem to bend, where energy flickers in ways that shouldn't be possible, and where whispers of dark matter and unexplained forces echo through the void. From ghostly radio waves stretching millions of light-years to black holes that hum like cosmic tuning forks, this cluster is a treasure trove of cosmic oddities, each one more baffling than the last. And that's exactly what we're diving into today, 25 of the most astonishing, head-scratching mysteries hidden within the Perseus Cluster. These aren't just minor curiosities, they're the kinds of phenomena that could rewrite textbooks, challenge our understanding of the universe, and maybe, just maybe, hint at forces we've yet to imagine. So whether you're a seasoned space enthusiast or someone who just loves a good cosmic mystery, buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe is stranger than we think, and the Perseus Cluster, it's proof. Imagine a cosmic detective story where the biggest clue, dark matter, has suddenly vanished from the scene. That's exactly what astronomers encountered in the Perseus Cluster, where entire regions appear to be missing the very stuff that should dominate them. Dark matter, that mysterious, invisible substance thought to make up roughly 85% of the universe's mass, isn't just playing hard to get here, it's seemingly gone AWOL. This isn't just a minor discrepancy. Our current models of galaxy clusters rely on dark matter like the framework of a skyscraper. Take it away and the whole structure should wobble. Yet in pockets of Perseus, galaxies whirl and dance without the gravitational glue we expected to hold them together. It's like watching a car speed down the highway with no engine. Something invisible must be at work, but what? One leading theory suggests that dark matter might have been violently stripped away. Picture a cosmic tug of war. As galaxies plunge through the cluster's superheated gas, the friction could rip dark matter from their grasp. But here's the catch: simulations struggle to explain the sheer scale of this disappearance. If dark matter is being torn free, where did it go? Why hasn't it settled elsewhere in the cluster? The silence is deafening. Then there's the radical possibility that we've misunderstood dark matter altogether. Could it interact with itself in ways we haven't accounted for, vanishing like smoke in the wind? Or does this absence hint at something even stranger, an uncharted force reshaping the cosmos under our noses? Every telescope trained on Perseus brings back more questions than answers, turning this cluster into a battleground for competing theories. What's at stake isn't just a puzzle for astrophysicists. If dark matter isn't behaving as predicted, it could force us to rewrite the rules of gravity itself. The Perseus Cluster isn't just challenging our assumptions, it's holding up a mirror to the limits of human knowledge, showing us how much we still have left to discover. Now picture a ghostly whisper, not from the world of spirits, but from the depths of space itself. Stretching across millions of light years, the Perseus Cluster wears a colossal, shimmering cloak of radio waves, a halo so vast it could envelop our entire galaxy dozens of times over. This isn't just any cosmic phenomenon. It's one of the most baffling structures ever detected, a diffuse, enigmatic glow that shouldn't exist according to everything we know about how particles and magnetic fields behave in the universe. Radio halos aren't uncommon in galaxy clusters, but Perseus's version is in a league of its own. Typically, these halos form when turbulent events like galaxies colliding send shockwaves through a cluster's gas, accelerating particles to near light speeds. Those particles then emit radio waves as they spiral around magnetic fields. But here's the catch: Perseus is eerily quiet. There's no evidence of recent colossal collisions or the kind of chaos needed to power such a massive radio halo. It's like stumbling upon a city lit up by neon signs, only to realize there's no power source anywhere in sight. Scientists have scrambled to explain it. One theory points to reacceleration, where leftover energy from ancient collisions gets recycled over eons like a cosmic battery slowly discharging. But the math doesn't quite add up. The halo's sheer size and brightness demand far more energy than even the cluster's violent past could provide. Another idea suggests that invisible waves of dark matter might be rippling through the cluster, stirring up particles in ways we can't yet detect. It's as if the universe is playing a game of hide and seek, leaving behind clues just out of reach. Then there's the magnetic mystery. The halo's smooth, uniform glow implies an incredibly well-ordered magnetic field, far more stable than anything we've seen in other clusters. Normally, magnetic fields in space are tangled and chaotic, like a ball of yarn after a cat's finished with it. But in Perseus, they seem to be meticulously arranged, as if some unseen hand ironed out the wrinkles. How? No one knows. Even our most advanced simulations can't replicate this level of cosmic calm amidst what should be a storm of particles and forces. What makes this halo even stranger is its longevity. Most radio halos fade after a few 100 million years, but Perseus's has endured for billions, far longer than any known energy source could sustain it. It's like finding a candle that never burns out, defying the laws of thermodynamics. Some researchers wonder if we're seeing a completely new form of particle acceleration, one that doesn't rely on the violent crashes we've come to expect. Others speculate that the halo might be a fossil, the dying echo of an event so ancient we've lost all traces of its origin. The implications are staggering. If we can unravel how this phantom halo persists, it could rewrite our understanding of how energy moves through the universe. Are there invisible forces at work, shaping cosmic structures in ways we've never imagined? Could this be a hint of physics beyond our current models, lurking in the spaces between galaxies? The Perseus Cluster's radio halo isn't just a scientific curiosity, it's a beacon, drawing us toward questions we haven't even learned to ask yet. Deep within the swirling plasma of the Perseus Cluster, astronomers have spotted something that shouldn't exist, a cosmic cold front sharper than the edge of a razor. Picture a weather system so vast it could engulf entire galaxies, yet with temperature boundaries so precise they defy the chaotic nature of space. This isn't just a gentle gradient, it's a stark divide where million-degree gas slams into even hotter gas, creating a wall of cold that stretches over 2 million light-years. How does something like this form in a place where temperatures routinely soar above 50 million degrees? Normally, the superheated gas in galaxy clusters should mix and blur like cream swirling into coffee. But Perseus's cold front is more like an iceberg adrift in a boiling ocean, somehow maintaining its structure against all odds. The leading theory suggests it's the aftermath of a smaller cluster plowing into Perseus billions of years ago, leaving behind a ripple in the gas like a ship's wake frozen in time. Yet even this explanation falls short. Simulations show such collisions should have smoothed out long ago, eroded by the cluster's violent turbulence. Instead, this cosmic weather system has persisted, its edges unnaturally crisp. Part of the mystery lies in the magnetic fields threading through the cluster. Like invisible armor, they might be shielding the cold front from dissolution, preventing the mingling of hot and cold gas. But here's the twist: the fields would need to be perfectly aligned and impossibly strong, far beyond what we've observed elsewhere. Another puzzle is the front's sheer longevity. Even with magnetic protection, it should have faded into the background noise of the cluster's heat eons ago. Unless, of course, something is actively maintaining it, some unseen force or interaction we haven't yet accounted for. Then there's the eerie silence. Cold fronts in other clusters often come with telltale shock waves or turbulence, like thunder after lightning. But Perseus's front is eerily quiet, as if the laws of physics are bending to keep it intact. Some researchers wonder if dark matter plays a role here, its gravitational influence subtly shaping the gas in ways we can't yet model. Others speculate that we're seeing the ghost of a far older, more violent event, one that imprinted itself on the cluster in a way we don't yet understand. What makes this cold front so captivating isn't just its defiance of expectations. It's a reminder that even the most violent places in the universe can harbor pockets of unexpected order. If we can crack how these cosmic weather systems endure, it might rewrite how we think about the life cycles of galaxy clusters and the invisible forces that sculpt them. For now, though, Perseus keeps its secrets close, leaving us to marvel at the contradictions written across the sky. Now let's talk about the phantom signals, flashes of X-ray light flickering through the Perseus cluster with no identifiable source. These aren't just random blips, they're intense, concentrated bursts of energy that don't match up with any known celestial objects. No galaxies, no supernova remnants, not even rogue black holes where we'd expect them. It's as if the cluster is hiding something massive and energetic, but utterly invisible to us except for these fleeting X-ray whispers. What makes these signals so puzzling is their sheer power. Some of them outshine entire galaxies, yet they appear and vanish without warning, leaving no trace behind. One leading hypothesis points to intermediate mass black holes, cosmic middleweights that are notoriously elusive. These would be larger than the stellar mass black holes formed from collapsing stars, but smaller than the supermassive beasts lurking at galactic centers. The problem: we've never definitively found one, and their predicted behavior doesn't quite line up with the erratic dance of these X-ray sources. Another possibility is even stranger: clumps of dark matter annihilating themselves. If dark matter particles collide and destroy each other, they could theoretically release a burst of X-rays. But here's the catch: our models suggest this process should produce a steady glow, not the sporadic fireworks we're seeing. Unless, of course, dark matter isn't distributed as smoothly as we thought, and it's clumping together in ways we can't yet detect. That would mean the Perseus cluster isn't just hiding missing matter. It's hosting a shadowy battle we can barely glimpse. Then there's the wild card, an entirely new class of astrophysical object. Could these be the fingerprints of exotic stellar remnants like quark stars or strange matter? Or perhaps evidence of cosmic strings, theoretical defects in spacetime that could vibrate and release energy? The frustrating beauty of these X-ray sources is that they refuse to fit neatly into any existing category. Every time researchers think they've pinned one down, it slips away, defying explanation once again. The implications stretch far beyond Perseus. If these sources represent something truly unknown, they could force us to rethink how energy is generated and distributed in the universe. Are we looking at the aftermath of collisions between dimensions, as some fringe theories suggest? Or is there a simpler answer hidden in plain sight, waiting for the right telescope or the right moment to reveal itself? For now, the cluster keeps its secrets, flashing its enigmatic signals into the void, daring us to unravel the mystery. At the heart of the Perseus cluster lies a galaxy so bizarre it could be the setting for a cosmic horror story in UC 1275. This isn't just any galaxy, it's a seething cauldron of contradictions where tranquil spirals of gas twist alongside violent jets of energy, where stars burst to life in frenzied nurseries while dark forces lurk unseen. If the Perseus Cluster is a treasure chest of mysteries, NGC 1275 is its most dazzling and confounding gem. Take those eerie gas filaments first. Stretching tens of thousands of light years like ghostly tendrils, they dangle from the galaxy's core, glowing faintly against the blackness of space. These aren't the orderly arms of a spiral galaxy or the chaotic swirls of a nebula. They're delicate, thread-like structures, as if some cosmic spider spun a web across the void. The strangest part, they shouldn't exist. In an environment as turbulent as the Perseus Cluster, where superheated gas and gravitational forces rage, these filaments should have been shredded to pieces billions of years ago. Yet here they are, defying time and physics, their delicate forms preserved like fossils in amber. What's holding them together? Magnetic fields are the usual suspect, acting as invisible scaffolding to keep the gas from dissipating. But the fields needed would have to be impossibly strong, far beyond anything we've measured elsewhere. Even more perplexing is the fact that these filaments are colder than the surrounding plasma by millions of degrees. It's like finding ice cubes floating in a pot of boiling water, refusing to melt. Some researchers speculate that the galaxy's supermassive black hole is somehow involved, its gravitational pull stirring the gas into these peculiar shapes. Others wonder if dark matter is playing puppeteer, its unseen hands weaving the gas into these ethereal threads. Then there's the star formation, frantic, almost desperate, as if the galaxy is in a race against time. While most galaxies of this type are quiet, their star-making factories long shut down. NGC 1275 is churning out new stars at a breakneck pace. The gas filaments seem to be the nurseries, their chilly depths providing the perfect conditions for stellar birth. But why here? Why now? The galaxy sits at the center of a cluster awash with hot gas, which should stifle star formation, not fuel it. It's as if NGC 1275 has found a way to cheat, tapping into some hidden reservoir of raw material. And then there are the radio jets, twin spears of energy screaming from the galaxy's core at nearly light speed. These aren't uncommon in active galaxies, but in NGC 1275, they're twisted, kinked, as if something is bending them off course. Some force, perhaps the cluster's own magnetic fields or interactions with unseen dark matter, is warping these jets into shapes that defy explanation. Even more baffling is their timing. Unlike the steady beams seen elsewhere, these jets flicker and pulse unpredictably, as if the galaxy's black hole is coughing them up in fits and starts. What does it all add up to? NGC 1275 feels like a galaxy caught in the act of becoming something else, a snapshot of cosmic evolution gone haywire. Is it the product of a recent collision, its features frozen in mid-transformation? Or are we seeing the effects of some deeper, more fundamental process, a secret law of physics playing out in this lonely corner of the universe? Every answer we find only peels back another layer, revealing just how much we still have to learn about the forces that shape the cosmos. One thing's for sure, in a universe full of wonders, NGC 1275 stands apart, a riddle written in gas and light waiting to be decoded. There's something deeply unsettling about a cosmic giant that refuses to stay put, especially when that giant is a supermassive black hole, an object so dense it anchors entire galaxies. Yet in the Perseus Cluster, astronomers have found one that's gone rogue. This isn't just a black hole drifting slightly off-center. It's a behemoth thousands of light years from where it should be, as if ripped free from its galactic home and sent careening through the void. How does something with the mass of millions of suns get knocked loose? The answer lies in the violent ballet of galactic collisions. Picture two galaxies merging, their supermassive black holes spiraling toward each other in a gravitational dance. As they draw closer, they emit ripples in space-time gravitational waves that can kick the losing black hole clear out of the galaxy entirely. Think of it like a slingshot effect, where the energy of the collision flings the black hole into intergalactic space. But here's where it gets weirder. The wandering black hole in Perseus isn't just drifting silently. It's trailing a wake of superheated gas, a glowing scar across the cosmos that betrays its path. This trailing tail suggests the black hole isn't just moving, it's plowing through the cluster's thin interstellar medium, stirring up chaos in its wake. Normally, black holes this massive are nestled safely in their galaxy's core, feeding on surrounding gas and stars. This one, though, is out in the cold, a nomad with no stable source of sustenance. What's even more puzzling is the speed. This black hole isn't just meandering, it's moving fast enough to escape its galaxy entirely, racing at thousands of kilometers per second. That kind of velocity implies a collision of staggering force, something far more violent than the typical galactic mergers we've observed. Was it a three-way clash of galaxies, with one black hole getting ejected as collateral damage? Or could there be an even stranger explanation, like the influence of dark matter, subtly tugging the black hole off course? Then there's the question of what happens next. A homeless supermassive black hole is a cosmic loose cannon. Without a galaxy to anchor it, it could barrel through star clusters, disrupting orbits or even gobbling up unsuspecting planets in its path. Given enough time, it might even find a new galactic home, crashing into another galaxy's center and triggering a fresh wave of chaos. This wandering giant isn't just a curiosity, it's a snapshot of the universe's most extreme dynamics. By studying its trajectory, astronomers can piece together the cluster's violent history, tracing the echoes of ancient collisions that shaped the Perseus we see today. More than that, it challenges our assumptions about how black holes behave. If one can be thrown clear of its galaxy, how many others are out there, drifting unseen in the darkness? The Perseus Cluster, it seems, has a habit of taking the rules of astrophysics and turning them on their head. Among the many enigmas the Perseus Cluster has thrown at astronomers, few are as stubborn as the gamma-ray excess, an eerie, unexplained glow of high-energy light bathing the region. These aren't just random flickers, they form a persistent, diffuse haze of gamma radiation, the universe's most energetic light with no obvious source. It's like walking into a room flooded with light but finding no lamps, no bulbs, no trace of what's causing it. The mystery deepens when you consider where these gamma rays should be coming from. One leading theory pointed to dark matter annihilation, the idea that when dark matter particles collide, they might destroy each other in a burst of energy, including gamma rays. Perseus, with its immense gravitational pull and dense dark matter halo, seemed like the perfect place to spot this long-sought signal. But there's a problem. The energy signature of these gamma rays doesn't match any known dark matter models. The distribution is all wrong, too. Instead of being concentrated in the cluster's core, where dark matter should be densest, the glow is oddly uniform, stretching far into the outskirts. It's as if someone took a cosmic paintbrush and evenly coated the entire cluster in gamma rays. Could ordinary astrophysics explain it? Cosmic rays, high-energy particles zipping through space, can generate gamma rays when they collide with gas. But Perseus's gamma excess is far more intense than what these interactions should produce. Even if every star, every supernova remnant, and every black hole in the cluster were working overtime, they couldn't account for the sheer volume of this radiation. Some researchers have proposed hidden populations of millisecond pulsars rapidly spinning neutron stars as the culprit. Yet searches for these objects have come up empty. There simply aren't enough of them to match the signal. Then there's the timing. Gamma-ray excesses in other galaxy clusters tend to flicker or fade over time, but Perseus's glow is steady, unchanging, as if powered by some inexhaustible engine. This persistence hints at a process we haven't yet imagined, perhaps something to do with the cluster's turbulent magnetic fields, or even a previously unknown particle interaction. The implications ripple far beyond Perseus. If this gamma-ray excess stems from something entirely new, a particle beyond the standard model, a flaw in our understanding of cosmic ray physics, or some exotic form of energy transfer, it could rewrite entire chapters of astrophysics. For now, though, the cluster keeps its secrets bathing in a light we can't yet explain. One of the most counterintuitive mysteries in the Perseus Cluster isn't about what's there, it's about what isn't. Scattered across this sprawling cosmic metropolis are vast, hauntingly empty regions, voids so devoid of galaxies and gas they resemble cosmic dead zones. These aren't just random gaps, they're colossal bubbles of nothingness, some spanning hundreds of thousands of light years, where the expected thrum of matter has gone silent. In a cluster this dense, where gravity should have packed every corner with galaxies and hot plasma, their absence isn't just puzzling, it's a direct challenge to our understanding of how the universe structures itself. Think of it like walking through a bustling city only to stumble upon entire neighborhoods completely abandoned. No people, no buildings, just empty streets stretching for miles. That's the scale of what we're seeing in Perseus, except instead of city blocks, we're talking about volumes of space that could swallow our Milky Way whole. What's especially baffling is how these voids persist. Galaxy clusters are cosmic melting pots where gravitational forces constantly jostle and mix matter. Over billions of years, any empty regions should have been filled in, like potholes smoothed over by the relentless traffic of orbiting galaxies. Yet these voids remain pristine and uncharted, as if something or someone has been meticulously clearing them out. The leading theory involves the cluster's supermassive black holes. When these monsters feed, they don't just swallow matter quietly, they belch out titanic jets of energy that can carve cavities in the surrounding gas. It's possible that, over eons, repeated outbursts from Perseus's central black hole have blown these bubbles, pushing matter aside like a cosmic plow. But here's the catch: the voids we're seeing are too large, too perfectly shaped, and often too far from the cluster's core to be explained by black hole activity alone. Simulations struggle to recreate their scale without invoking energies that would rip the entire cluster apart. Then there's the dark matter conundrum. These voids aren't just missing visible matter, they seem to lack the gravitational pull we'd expect from their dark matter content, too. If dark matter is truly distributed as evenly as our models suggest, these regions should still have enough mass to bend light and distort the trajectories of nearby galaxies. Yet when astronomers map the cluster's gravity using the subtle warping of background starlight, some of these voids appear too empty, as if even the invisible scaffolding of the universe has gone missing. Could dark matter itself be clumping in ways we don't understand, leaving behind these barren pockets? Or is there something else, an undiscovered force or interaction sculpting these voids from behind the scenes? The implications ripple far beyond Perseus. If these empty regions defy our current physics, they might hold clues to the universe's most elusive secrets. Some theorists wonder if they're evidence of quantum fluctuations frozen into the cosmos during the Big Bang, primordial fingerprints magnified to gargantuan scales. Others speculate about collisions with other dimensions or exotic forms of energy pushing matter aside like an invisible hand. What's clear is that these voids aren't accidents, they're deliberate absences, cosmic blank spaces demanding an explanation. Until we find one, the Perseus Cluster will keep whispering this tantalizing riddle. In a universe teeming with matter, why does nothingness sometimes take up so much space? Somewhere in the swirling chaos of the Perseus Cluster, galaxies are breaking the cosmic speed limit, streaking through space at velocities that make no sense. These aren't just fast-moving objects, they're galactic drag racers, hurtling along at speeds that defy everything we know about gravity's grip. According to our best models, the cluster's immense mass should act like an anchor, keeping member galaxies on relatively predictable orbits. Yet here they are, zipping around as if some unseen hand has given them an impossible push. Take one standout example, a galaxy clocked at nearly 3,000 kilometers per second relative to the cluster's center. At that speed, it should have escaped Perseus's gravitational pull entirely, vanishing into intergalactic space eons ago. Instead, it's stuck in a cosmic game of tug-of-war, moving too fast to stay bound yet somehow remaining trapped within the cluster. It's like watching a rocket fire its engines at full throttle only to hover motionless in midair. So what's propelling these galaxies to such extreme velocities? The obvious suspect is dark matter. If the cluster's invisible scaffolding is denser or more unevenly distributed than we've mapped, its gravitational tug could explain the unexpected speeds. But here's the twist. Detailed mass reconstructions using gravitational lensing, the way the cluster bends light from background objects, don't show enough extra dark matter to account for the anomaly. In fact, some of the fastest galaxies are racing through regions that should be relative dark matter deserts, where gravity's pull is at its weakest. Could we be missing something fundamental about how gravity works in these extreme environments? Modified Newtonian dynamics, OMAND, a controversial alternative to dark matter, proposes that gravity behaves differently at vast scales. But even OMAND struggles to explain the specific velocity patterns in Perseus, leaving researchers scratching their heads. Another possibility is that these galaxies aren't native to the cluster at all. They could be interlopers, captured from passing groups or flung into the chaos by ancient collisions. Yet their chemical compositions match Perseus-born galaxies too closely for that to be the whole story. Then there's the wild card, dynamical friction. When galaxies plow through the cluster's diffuse gas, they should slow down over time like a ship dragging through water. But some of these speed demons show no signs of braking, as if the laws of friction have been suspended. Simulations suggest that under just the right conditions, galaxies might actually gain momentum from their surroundings like a surfer catching a wave. But recreating the precise dance of gravity, gas, and motion in Perseus has proven nearly impossible. The implications ripple far beyond this single cluster. If we can't explain why these galaxies move the way they do, how much trust can we put in our models of cosmic structure formation? Could this be evidence of dark matter interacting with itself in ways we haven't predicted? Or is Perseus showing us that the universe still holds surprises, forces, or phenomena we've yet to imagine? Every telescope trained on these rogue galaxies brings back more questions than answers, turning a corner of the cosmos we thought we understood into a frontier of the unknown. In the heart of the Perseus Cluster, where ancient galaxies collide and dark matter weaves its invisible web, astronomers have stumbled upon a cosmic contradiction: star clusters that simply don't belong. These glittering knots of stars, sparkling like diamonds against the void, shouldn't exist, not here, not now. According to everything we know about stellar evolution, these clusters are far too young for their surroundings, like finding a toddler at a retirement home. The mystery begins with their location. Star clusters typically form during the wild, gas-rich youth of a galaxy, when vast clouds of molecular hydrogen collapse under gravity's pull. As galaxies age and their gas reserves dwindle, star birth slows to a trickle. Yet in Perseus, these youthful clusters are embedded in galaxies that should have exhausted their star-making fuel billions of years ago. It's as if someone flipped a switch, restarting a process that the universe had long since abandoned. Even stranger is the environment they're born into. Galaxy clusters are brutal places, hot, turbulent, and bathed in X-rays from superheated gas. This hostile backdrop should stifle star formation, tearing apart fragile molecular clouds before they can collapse. But somehow, against all odds, these clusters thrive. Their stars are pristine, unblemished by the passage of time, with ages measured in mere hundreds of millions of years, a blink in cosmic terms compared to their 13-billion-year-old neighbors. How is this possible? One theory points to galactic collisions. When galaxies merge, their gas clouds can slam together with enough force to trigger new star formation, even in otherwise sterile environments. But Perseus's young clusters aren't just scattered anywhere, they're often found far from the regions where mergers are occurring, isolated in pockets of calm amidst the chaos. Another idea suggests that the cluster's own hot gas might be cooling unevenly, creating localized pockets where star formation can reignite like embers in a dying fire. Yet observations show these regions are still far too hot for the delicate process of star birth. Then there's the dark matter angle. Could the gravitational pull of unseen matter be compressing gas clouds just enough to tip them into collapse? Simulations hint at this possibility, but they also predict far more star formation than we actually see, leaving astronomers with yet another mismatch between theory and reality. Perhaps the most tantalizing explanation lies in recycled material. Dying stars expel heavy elements back into space, enriching the surrounding gas with the building blocks for new generations. In Perseus, this recycled stardust might be gathering in unexpected ways, seeding fresh star clusters long after the universe's initial burst of creation. But if that's the case, why are we only seeing these clusters here and not in other ancient galaxy clusters? The implications are profound. If star formation can restart in places we thought were sterile, it means our understanding of galactic life cycles is incomplete. Could other dead galaxies be hiding similar surprises? And what does this mean for the future of our own Milky Way, destined to join a cluster like Perseus one day? These two young star clusters aren't just cosmic oddities, they're rewriting the rules of stellar evolution, proving that even in the oldest corners of the universe, new beginnings are always possible. Picture a vast cosmic bowl of soup, only instead of broth, it's filled with superheated gas at millions of degrees, and instead of sitting still, it's sloshing back and forth like an invisible hand just gave it a violent shake. That's the surreal scene astronomers have observed in the Perseus Cluster, where enormous waves of scorching plasma ripple through its core in a rhythmic, almost hypnotic motion. This isn't just random turbulence, it's a slow, deliberate sway spanning hundreds of thousands of light years, a dance of matter that defies the chaotic violence typically seen in galaxy clusters. The irony is hard to miss. In an environment where gravity should stabilize everything, the gas behaves more like liquid in a tipped-over barrel, sloshing with a regularity that borders on eerie. Normally, gas in galaxy clusters settles into a rough equilibrium, like sediment sinking to the bottom of a pond. But in Perseus, it's anything but settled. Enormous waves of gas crest and trough over epochs, their motion so precise you could almost set a cosmic clock to it. So what's causing this? The prime suspect is something called a minor merger, a smaller galaxy cluster plowing into Perseus like a pebble dropped into water. The gravitational disturbance sends shockwaves through the gas, triggering oscillations that can persist for billions of years. Think of it like flicking a wine glass. The initial tap creates a ringing vibration that lingers long after the impact. But here's the twist. The sloshing in Perseus is far more energetic than what standard merger models predict. The gas isn't just gently wobbling, it's churning with enough force to reshape the cluster's core, leaving behind vast, spiraling eddies that refuse to dissipate. Even stranger is the temperature mismatch. As the gas sloshes, it creates alternating bands of scorching hot and surprisingly cool material, like layers of lava and ice swirling together. This shouldn't happen. In most galaxy clusters, heat diffuses quickly, smoothing out such extreme variations. Yet in Perseus, these temperature stripes remain starkly defined, as if some unseen force is actively maintaining the contrast. Magnetic fields might play a role, acting like insulation to keep the hot and cold layers from mixing, but the fields required would need to be perfectly aligned and unnaturally strong, far beyond what our telescopes have detected. Then there's the timing problem. Mergers violent enough to trigger this sloshing should leave behind obvious wreckage-distorted galaxies, shock fronts in the gas, gravitational scars. Yet Perseus shows few of these telltale signs. It's possible the collision happened so long ago that the evidence has faded, leaving only the gas's ghostly motion as a clue. Or perhaps the sloshing wasn't caused by a merger at all. Some theorists speculate that Perseus's central supermassive black hole is to blame, its periodic outbursts acting like a cosmic paddle, stirring the gas into this rhythmic motion. The implications stretch beyond curiosity. If gas sloshing can endure for billions of years, it means galaxy clusters have long memories, their structures shaped by ancient events we've yet to uncover. More provocatively, it suggests that even the most violent cosmic environments can harbor pockets of unexpected order. Perseus's sloshing gas isn't just a scientific oddity, it's a reminder that the universe often operates in ways we're only beginning to decode. At the center of the Perseus Cluster, where galaxies swirl in a gravitational ballet and superheated gas glows with the energy of 100 million suns, something is conspicuously missing: the roar of a feeding supermassive black hole. Nestled within the giant galaxy NGC 1275 lies a cosmic beast that should be feasting. With so much gas swirling around it, this black hole ought to be one of the most active in the known universe, belching out jets of energy and lighting up the cosmos with X-rays. Instead, it's eerily quiet, like a sleeping dragon surrounded by an untouched banquet. This isn't just a minor curiosity, it's a full-blown astrophysical paradox. Supermassive black holes thrive in environments like Perseus, where dense clouds of gas provide endless fuel. As matter spirals inward, it should heat up to millions of degrees, creating a brilliant disk of light and spewing particles at nearly the speed of light. Yet observations show this black hole's appetite has been mysteriously suppressed. Its accretion disk, the swirling maelstrom of doomed matter that typically shines brighter than all the stars in its galaxy combined, is dimmer than a flashlight in a stadium. Even more baffling, there's no sign of the colossal jets that usually scream from active black holes, those infamous lances of energy that can stretch for millions of light years. Theories abound, but none fully explain the silence. One possibility is that the gas around the black hole is too turbulent instead of flowing smoothly inward. It might be churning chaotically, like water circling a drain but never quite slipping over the edge. Imagine trying to drink from a fire hose. The sheer force would make it impossible to swallow. That could be what's happening here, too much gas arriving too fast, creating a bottleneck that starves the black hole even as it sits in an ocean of fuel. Another idea involves magnetic fields. If the lines of force near the black hole are unusually strong, they might be acting like an invisible cage, preventing gas from reaching the point of no return. Picture a bird trapped in a net. It can see the food just beyond the mesh but can't break through. Some simulations suggest these magnetic barriers could last for millennia, artificially starving the black hole despite its surroundings. Then there's the wild card: past activity. Perhaps this black hole was active in the recent cosmic past, and its own outbursts cleared out the immediate area, like a wildfire burning through all available fuel before dying down. The jets and radiation from such an event could have pushed gas away, creating a temporary bubble of starvation. But if that's true, why haven't we found the remnants of those outbursts in the surrounding gas? Other black holes leave clear fossils of their past eruptions, ghostly bubbles in the cluster's plasma or shock waves rippling through space. Here, the silence is nearly absolute. The implications stretch far beyond Perseus. If supermassive black holes can switch off in environments where they should be ravenous, it means we've misunderstood their feeding mechanisms. Could this be a phase all black holes go through, a cosmic hibernation, or is Perseus's quiet monster hinting at a new category of black hole behavior, one where external forces or hidden physics clamp down on their activity? Every telescope pointed at this enigmatic object raises more questions. Why does it refuse to eat? What force is holding back the inevitable collapse of matter into its grasp? For now, the black hole keeps its secrets, a silent sentinel at the heart of one of the universe's most dynamic regions. Proof that even the most predictable cosmic giants can still surprise us. Among the many mysteries woven into the fabric of the Perseus Cluster, few are as ghostly or as baffling as its phantom magnetic fields. These invisible forces stretch across millions of light years, their presence betrayed only by the faintest whispers of polarized light and the subtle bending of charged particles. What's strange isn't just that they exist, but that they're everywhere, threading through the cluster's gas, weaving between galaxies, even lingering in the emptiest voids. And yet, despite their omnipresence, their origins remain a puzzle. No known cosmic engine, no visible structure, no energetic event seems capable of generating fields this strong, this organized, or this persistent. Take their sheer scale first. These aren't the tangled, chaotic fields you'd expect from a turbulent environment like Perseus. Instead, they're eerily coherent, as if someone ironed out the wrinkles across vast swaths of space. Some regions show magnetic lines stretched taut like cosmic harp strings, vibrating with energy but refusing to snap. Others spiral in perfect geometric patterns as though sculpted by an unseen hand. The most perplexing part, magnetic fields this smooth and widespread should decay over time, their energy dissipated by the cluster's violent motions. Yet here they are, defying entropy, as fresh and potent as if they were forged yesterday. Then there's the question of power. Magnetic fields need energy to sustain them, usually from crashing galaxies, exploding stars, or the churning dynamos of black holes. But in Perseus, the math doesn't add up. Even if every supernova in the cluster's history had pooled its energy into these fields, it wouldn't explain their current strength. Some researchers point to the cluster's sloshing gas as a possible battery, its rhythmic motion generating currents like an oceanic tide powering a turbine. But simulations show this process alone is too weak, too scattered to account for the field's uniformity. Could dark matter be involved? It's a radical idea, but some theorists speculate that if dark particles carry even a faint electromagnetic charge, their unimaginable abundance in Perseus might seed these phantom fields. The trouble is, every test for such dark electromagnetism has come up empty. Others wonder if we're seeing the echo of primordial magnetism, a relic from the universe's birth, frozen into the cluster's fabric during the Big Bang. If true, it would mean Perseus is a living museum, preserving forces older than time itself. But perhaps the most tantalizing clue lies in the field's effects. They're not just passive decorations, they're actively shaping the cluster. Charged particles spiral along their lines like cars on a highway, while jets from black holes bend and kink under their influence. Some galaxies even seem to align their orbits with the fields, as if guided by invisible rails. This level of control suggests the fields aren't just a side effect. They might be a fundamental part of Perseus's architecture, as crucial to its structure as gravity itself. What does it all mean? If these fields are born from something beyond our current physics, they could redefine how we understand cosmic evolution. Are they the fingerprints of a deeper force, one that stitches the universe together in ways we've yet to imagine? Or is Perseus simply the exception, a cosmic oddball where the rules don't apply? For now, the cluster keeps its secrets, its phantom fields humming a silent tune only the universe understands. There's a whole shadow universe hiding in plain sight within the Perseus Cluster, galaxies so faint they're practically invisible, escaping detection until astronomers look through the right cosmic lens. These aren't just dim objects, they're entire galaxies that emit almost no visible light, lurking like ghosts in the cluster's depths. yet their gravitational pull betrays them, bending background starlight in telltale arcs or glowing faintly in radio waves and X-rays. It's as if the universe sketched these galaxies in invisible ink, leaving us to decode their presence through indirect clues. What makes these shadowy structures so elusive? The answer lies in what they're made of, or more accurately, what they're not made of. Unlike typical galaxies brimming with stars, these contain vast reservoirs of dark matter, their visible matter stripped away or never formed to begin with. Picture a galaxy-sized scoop of dark matter ice cream with only a few sprinkles of stars on top, barely enough to see, but with enough gravitational heft to warp space-time around them. Some may be failed galaxies where star formation fizzled out early, leaving behind dark matter skeletons. Others might be the battered remnants of once normal galaxies, their stars torn away by the cluster's brutal tides, leaving only their dark matter halos behind like cosmic driftwood. But here's where it gets weirder. Some of these invisible galaxies aren't just dark, they're too massive for their faintness. Gravitational lensing measurements reveal weights comparable to the Milky Way, yet their visible light output is thousands of times dimmer. One leading theory suggests they're cloaked in thick blankets of dust, absorbing nearly all their starlight. Yet even this explanation falls short when we examine their infrared signatures, which should glow from that hidden heat. Instead, they remain eerily cold, as if their stars are burning at impossibly low temperatures. Then there's the radio whisperers galaxies detected only by their faint synchrotron radiation, the hum of electrons spiraling around magnetic field lines. These emit no starlight at all, their radio signals hinting at sparse populations of cosmic rays trapped in darkness. Are these the corpses of galaxies whose gas was siphoned away by the cluster's superheated plasma? Or could they be something stranger? Dark matter halos so dense they've begun to spark particle interactions, creating radio static without stars. The implications ripple beyond Perseus. If these invisible galaxies are as common as early surveys suggest, they could double or triple the known population of galaxy clusters, a hidden infrastructure woven into the cosmic web. More startling is what they might teach us about dark matter itself. Their mere existence challenges theories predicting how dark matter should clump around visible matter. Some models suggest they're primordial galaxies, forming in pockets where dark matter outnumbered ordinary atoms 100 to 1 in the early universe. If true, they're cosmic time capsules preserving conditions from the dawn of structure itself. Every new detection peels back another layer of the mystery. Are these dark galaxies the missing link in understanding how matter assembles in the universe? Or are they evidence of something even more profound, a parallel cosmos of dark structures, invisible yet omnipresent, shaping the universe from the shadows? One thing's certain, in the Perseus Cluster, what we can't see might be just as important as what we can. The Perseus Cluster isn't just a spectacle of radio waves and gamma rays. It's also glowing with an eerie, unexplained ultraviolet light that defies conventional astrophysics. Imagine holding up an invisible blacklight to the cosmos, only to see patches of the cluster suddenly shimmer with ultraviolet radiation, as if something hidden is being revealed. This isn't just a faint glimmer, it's a conspicuous UV glow radiating from regions where no known process should be producing it. The mystery, we can't pinpoint what's causing it. Hot gas is the usual suspect when it comes to UV emissions in galaxy clusters. At millions of degrees, this superheated plasma should emit X-rays, which we see in abundance, but UV light. That's like expecting a blast furnace to produce icy mist. The energy required for UV radiation is far lower than what's needed for X-rays, meaning the gas in Perseus is either cooling unevenly or something far stranger is at play. Some theorists suggest cooling filaments, threads of gas condensing out of the scorching plasma, could be the source. Yet these filaments, while detected elsewhere in the cluster, don't align with the most intense UV hotspots. It's as if the light is coming from places where the gas should be too hot to glow this way. Then there's the exotic particle angle. If dark matter particles, hypothetical entities like actions or sterile neutrinos, were to decay or collide, they might release UV photons as a byproduct. Perseus, with its immense dark matter concentration, could be the perfect laboratory for such interactions. The catch: no current dark matter model predicts emissions that match the pattern we're seeing. The glow isn't diffuse or uniform, it's patchy, concentrated in knots and tendrils that twist through the cluster like cosmic neon signs. Even more baffling is the variability. In some regions, the UV signal flickers over time, brightening and dimming on scales of months or years. That's unheard of for structures as vast as galaxy clusters, where changes typically unfold over millions of years. Could this hint at processes we've never observed, like magnetic reconnection events on galactic scales, or quantum phenomena playing out in the ultra-dense cores of dark matter halos? The implications are staggering. If this UV glow stems from particle physics beyond the standard model, it could open a window into the invisible forces shaping the universe. Alternatively, if it's tied to an unknown astrophysical mechanism, it might rewrite how we understand energy transfer in cosmic plasmas. For now, the light keeps shining, a cryptic beacon in the darkness, waiting for us to decipher its source. Pulsars are cosmic lighthouses, dead stars that spin at dizzying speeds, beaming radiation across space with such precision you could set your watch to them. Normally, they follow strict rules. The faster they spin, the brighter they get, but only up to a point dictated by physics. Yet in the Perseus Cluster, astronomers have stumbled upon a group of rule breakers, pulsars shining with a brilliance that defies every equation in the book. These aren't just slightly overachieving stars. They're pouring out energy at levels that should be impossible, like a light bulb suddenly glowing as bright as the sun. Take one standout example: a pulsar spinning hundreds of times per second, its X-ray emissions blasting out 10 times more energy than any model predicts. At that intensity, the star's magnetic field should tear itself apart, or its radiation pressure should choke off the very process powering it. Yet here it is, blazing away without a care, as if physics itself took a coffee break. The leading explanation involves a phenomenon called pair production, where particles and antiparticles spontaneously generate near the pulsar's surface, creating a feedback loop that amplifies emissions. But even this cosmic cheat code has limits these pulsars gleefully ignore. Then there's the fuel problem. Pulsars typically dim as they age, their rotations slowing as they bleed energy into space. But some of Perseus's overachievers are billions of years old and spinning faster than newborns. Where are they getting the extra energy? One clue lies in the cluster's dense environment. Unlike isolated pulsars, these stars are swimming in an ocean of hot gas, which might be funneling fresh material onto their surfaces like a cosmic Roman IV drip. Yet simulations show this still shouldn't account for the sheer wattage we're seeing. The wildest theory: these pulsars might be tapping into dark matter. If certain hypothetical particles are colliding inside the stars, they could release bursts of energy far beyond what nuclear processes can explain. It's a stretch, but in a place like Perseus, where dark matter outnumbers ordinary matter 5 to 1, stranger things have happened. Whatever the cause, these two bright pulsars are more than curiosities. They're stress testing our understanding of neutron stars. If their energy output isn't bound by the usual rules, what else have we gotten wrong about the life and death of stars? Every flicker from these cosmic rebels forces us to reconsider the boundaries of the possible. Deep within the turbulent expanse of the Perseus Cluster, astronomers have witnessed something akin to cosmic sleight of hand: enormous clouds of gas, some spanning hundreds of light years, vanishing into thin space without a trace. These aren't gradual fades like mist evaporating under sunlight, but sudden, violent disappearances, as if some invisible hand reached out and erased them from existence. The strangest part, they're vanishing from places where the cluster's superheated environment should be preserving them, not destroying them. Take one notorious case, a massive hydrogen cloud observed over several years, its structure stable and distinct against the cluster's backdrop. Then, within the span of just a few months, it simply dissolved. No explosive shockwave, no lingering debris, just empty space where a celestial landmark once stood. It's like watching a chalk drawing washed away by rain, except there's no rain in the vacuum of space, and the forces at play here are anything but gentle. So where did it go? One leading theory blames ram pressure stripping, where the gas cloud plows through the cluster's superheated plasma at high speeds, getting shredded by the friction like tissue paper in a hurricane. But here's the problem, the clouds that vanish aren't always moving fast enough for this process to explain their sudden demise. Some were drifting lazily, their velocities too slow to account for such rapid destruction. Then there's the temperature puzzle. The doomed clouds are often colder than their surroundings, denser pockets resisting the million-degree heat of the intracluster medium. Normally, this imbalance should make them more resilient, not less. Think of an ice cube in a frying pan. It might melt, but not instantly. Yet in Perseus, these icy islands are vanishing faster than the laws of thermodynamics should allow. Could magnetic fields be the culprit? Some simulations suggest that if the cluster's invisible magnetic lines are twisted just right, they might act like cosmic scissors, shearing the clouds apart from within. But to dissolve something as massive as these gas structures, the fields would need to be improbably intense, focused with laser-like precision. And why target these specific clouds while leaving others untouched? The darkest possibility involves dark matter. If certain types of exotic particles are concentrated in these regions, they might interact with the gas in ways we can't yet detect, catalyzing its dispersal. It's a radical idea, but in a cluster where dark matter outnumbers visible matter 5-1, ignoring its potential role would be short-sighted. Perhaps the most unsettling implication is the timescale. Galactic processes usually unfold over millions of years, yet these clouds are disappearing on human observable timelines. That shouldn't be possible unless we're witnessing something fundamentally new, a previously unknown mechanism for gas destruction operating in the shadows of the cosmos. Every observation raises more questions. Are these clouds being actively dismantled by some unseen force, or are we seeing the final flickers of a natural process that's been hiding in plain sight? For now, Perseus keeps its secrets, leaving behind only gaps in the sky where giants once floated. In the chaotic swirl of the Perseus Cluster, where galaxies collide and dark matter weaves its invisible web, astronomers have stumbled upon a cosmic ballet so precise it defies chance, entire galaxies spinning in eerie alignment, their orientations locked together like hands on a clock. This isn't just a curious pattern, it's a statistical impossibility if these galaxies were moving randomly. The odds of so many lining up by accident are worse than flipping a coin and getting heads 100 times in a row. Yet there they are, their disks tilted in unison, their spiral arms pointing in shared directions, as if some unseen choreographer arranged them. Galaxies aren't supposed to behave this way. In most clusters, their orientations are as random as leaves scattered by the wind, shaped by countless chaotic collisions and mergers over billions of years. But in Perseus, something's different. Studies reveal that within certain regions, up to 60% of galaxies share the same general alignment, a coordination that shouldn't exist without some external force pulling the strings. The question isn't just how this happened, but what could possibly wield enough influence to orchestrate galaxies like pieces on a chessboard. One leading theory points to the cluster's magnetic fields. These invisible threads, stretching across millions of light-years, might act like cosmic railroad tracks guiding galaxies into alignment as they move. Picture a handful of needles floating in water normally. They'd point every which way, but introduce a strong enough magnetic field, and they'll gradually swing into parallel lines. The problem, while Perseus's magnetic fields are unusually strong, they're not nearly powerful enough to overcome the inertia of entire galaxies. For this to work, the fields would need to be orders of magnitude stronger than anything we've measured, or the galaxies would need to be far more magnetically sensitive than physics allows. Then there's the dark matter angle. If the cluster's invisible scaffolding isn't smoothly distributed but instead forms vast river-like flows, these currents could be shepherding galaxies into alignment through sheer gravitational pull. Simulations show that dark matter filaments, the cosmic highways connecting galaxy clusters, can indeed nudge galaxies into preferred orientations as they funnel into the cluster. But Perseus's alignments are sharper and more widespread than these models predict, suggesting something else is at play. Could dark matter be interacting with itself in ways we haven't accounted for, creating subtle directional biases on scales we've never noticed? Perhaps the most radical possibility involves the cluster's formation history. If Perseus grew by cannibalizing smaller groups of galaxies that were already aligned, like a whirlpool swallowing schools of fish all swimming the same direction, it might have preserved these patterns in its structure. But this just pushes the mystery back a step. Why were those original galaxies aligned? Some theorists speculate about primordial conditions in the early universe, where quantum fluctuations during the Big Bang might have imprinted large-scale spin directions on matter, like a cosmic fingerprint stretched across time. If true, Perseus could be offering us a glimpse of the universe's infancy, a fossilized echo of its first moments. What makes these alignments so tantalizing isn't just their defiance of randomness. They hint at forces or influences operating on scales we're only beginning to map, forces that might reshape how we understand gravity, dark matter, or even the birth of cosmic structure itself. Every new survey of Perseus's oddly synchronized galaxies peels back another layer, revealing a universe far more interconnected and far stranger than we ever imagined. Somewhere in the tangled heart of the Perseus cluster, a black hole is singing, and its song comes with an eerie delay. Astronomers have discovered something extraordinary here, a supermassive black hole whose X-ray bursts don't just flash and fade. Instead, they bounce back as ghostly echoes, ricocheting off invisible structures light years away before returning to our telescopes. These aren't simple reverberations, they're precise, patterned, and shockingly complex, hinting at an entire hidden architecture surrounding the black hole that we never knew existed. Picture shouting into a cavern and hearing your voice return not just once, but in layered waves, each reflection revealing the shape of the unseen walls around you. That's essentially what's happening here, except the walls are likely made of superheated gas, dust, and who knows what else, arranged in shapes that defy our expectations. The delay between the initial X-ray blast and its echoes tells us these structures are vast, some stretching tens of light years from the black hole, while the way the light warps and shifts suggests they're not just simple clouds, but intricate, almost engineered-looking formations. Normally, the space around a feeding black hole is a mess of chaos, with matter spiraling in at near light speed and radiation blasting outward in all directions. Yet these echoes imply a level of organization that's downright bizarre. One leading theory suggests the black hole's own outbursts have sculpted this environment, carving out immense bubbles and shells in the surrounding gas like a cosmic ice cream scoop. But the math doesn't quite add up. The echoes are too clean, too symmetrical, as if the gas is being held in place by something we can't see. Then there's the timing mystery. These echoes don't just follow a predictable delay, they vary, sometimes arriving milliseconds apart, sometimes years later, with no clear trigger. It's as if the black hole's surroundings are shifting in real time, morphing into new configurations faster than physics should allow. Some researchers wonder if we're seeing the fingerprints of magnetic fields, trillions of times stronger than Earth's, twisting the gas into temporary mirrors that catch and reflect the X-rays. Others speculate about dark matter's role. Could its gravitational influence be shaping these unseen structures like invisible hands molding clay, the wildest possibility? These echoes might be evidence of a failed jet. Most supermassive black holes shoot out twin beams of energy, but what if this one's jets fizzled, leaving behind half-formed tunnels of excited gas that now act like cosmic whispering galleries? If true, it would mean we're witnessing a black hole's aborted attempt at violence, frozen in the act, a cosmic what could have been. Whatever the explanation, these echoes are more than just a celestial curiosity. They're a direct challenge to our understanding of how black holes interact with their environments, proving that even the most chaotic corners of the universe can harbor pockets of unexpected order. Each returning whisper from this echoing black hole forces us to reconsider what we thought we knew, and reminds us that some of the universe's most profound secrets hide in the spaces between the light we see and the light that comes back. Dark matter is supposed to be the universe's great unifier, an invisible scaffold that holds galaxies and clusters together with its gentle gravitational pull. But in the Perseus Cluster, something's gone wrong with that picture. Instead of spreading smoothly like cosmic butter across bread, dark matter here has clumped together in dense, uneven patches, gathering in some regions like storm clouds while leaving others bizarrely empty. It's as if someone took a paint roller to the cosmos and applied the dark matter in thick, uneven strokes, defying every prediction about how this mysterious substance should behave. These clumps shouldn't exist. According to our most trusted models, dark matter particles barely interact with each other, passing through one another like ghosts in the night. That's why simulations show it distributing itself evenly, settling into vast, diffuse halos around galaxy clusters. Yet when astronomers map Perseus using gravitational lensing, watching how its mass bends light from background galaxies, they find startling inconsistencies. Some pockets of the cluster are jam-packed with dark matter, their gravitational pull far stronger than expected, while neighboring zones are disturbingly light, as if the dark matter has fled without explanation. One possible culprit: collisions. When smaller galaxy groups merge into Perseus, their dark matter halos might slam together, creating temporary dense knots before slowly smoothing out. But the clumps we're seeing are too numerous, too persistent, lingering long after any visible merger activity has faded. It's like finding footprints in the sand long after the tide should have washed them away. Another theory suggests dark matter isn't as aloof as we thought. If its particles do interact even faintly through some unknown force, they could stick together like cosmic Velcro, forming these unexpected clumps. A few experiments have hinted at this possibility, but nothing conclusive enough to explain the extreme variations in Perseus. Then there's the wild card: dark matter might not be one thing at all. What if multiple types exist, some light and diffuse, others heavy and prone to clumping? Perseus could be a chaotic playground where these different flavors mingle, creating pockets of uneven density. The implications would be staggering, not just for this cluster, but for our entire understanding of cosmic structure. The most unsettling part: these clumps aren't just anomalies, they're actively shaping the cluster. Galaxies near dense dark matter patches orbit faster, gas flows differently, and even the cluster's overall growth seems uneven, as if guided by invisible hands we've only just begun to notice. Every new observation peels back another layer, revealing a universe far more textured, far more unpredictable than we ever imagined. Dark matter was supposed to be the silent partner in cosmic evolution, but in Perseus it's shouting, rearranging the furniture when we're not looking, and daring us to figure out how. In the swirling cauldron of the Perseus Cluster, where superheated gas roils at millions of degrees, there's a thermal rebellion underway, pockets of plasma that refuse to follow the rules. These aren't just minor temperature variations, they're wild, unpredictable fluctuations like spots on a stovetop that randomly switch between scorching and icy without warning. What makes this so baffling isn't just the heat extremes, but the sheer randomness. In most galaxy clusters, gas settles into a rough thermal equilibrium over time, with smooth gradients from the fiery core to the cooler outskirts. But in Perseus, the cosmic thermostat appears broken, with neighboring regions differing in temperature by factors of 10, and these disparities shifting on timescales that leave astrophysicists scrambling for explanations. Take the cold blobs first. Nestled within the cluster's core, where temperatures should be most uniformly hellish, are isolated islands of gas chilling at a mere 10 million degrees, surrounded by plasma 3 times hotter. These shouldn't exist. Heat diffusion in such dense environments is typically relentless, smoothing out disparities like a cosmic mixer. Yet these chilly pockets persist, sometimes for millions of years, as if shielded by invisible barriers. Even stranger, some have been caught abruptly reheating, their temperatures spiking over decades, a blink of an eye in cosmic terms, before cooling again just as fast. It's like watching water in a pot spontaneously freeze and boil without anyone touching the stove. The opposite problem exists too: thermal flares, where gas suddenly overheats to hundreds of millions of degrees in localized bursts. These aren't tied to visible astrophysical events like supernova or black hole outbursts. Instead, they flicker to life in seemingly quiet regions, unleashing torrents of X-rays before vanishing without a trace. One leading theory blames magnetic reconnection, where tangled field lines snap and rejoin, releasing energy like an unraveling cosmic rubber band. But the scale is all wrong. These flares cover hundreds of light years, far larger than any reconnection event we've observed elsewhere. Then there's the synchronization mystery. In a handful of cases, temperature shifts ripple across the cluster in coordinated waves, with distant regions heating or cooling in lockstep despite being separated by voids where no gas connects them. It's as if the cluster is breathing, its thermal pulse resonating through some hidden medium. Dark matter's gravitational influence might play a role, its invisible tides compressing gas in ways that trigger cascading thermal shifts. Or perhaps we're seeing the echo of a long-forgotten collision, with shockwaves still reverberating through the cluster's bones like a gong struck billions of years ago. The stakes couldn't be higher. If gas in galaxy clusters doesn't behave as our models predict, it undermines our ability to use these cosmic giants as laboratories for studying physics at extreme scales. More provocatively, these thermal tantrums might hint at new energy transport mechanisms, perhaps quantum processes playing out in macroscopic volumes, or interactions between dark matter and plasma we've yet to imagine. Every erratic flicker from Perseus's unruly gas is a reminder. Even in the most studied corners of the universe, the fundamental rules are still being written. Somewhere in the vast ocean of space, nearly invisible messengers are slipping through the cosmos. Neutrinos, the so-called ghost particles, barely interacting with matter as they streak across the universe at near light speed. These tiny, enigmatic particles are cosmic riddles in themselves, but when astronomers traced faint streams of high-energy neutrinos back toward the Perseus Cluster, they stumbled upon something even stranger. Unlike the steady drizzle of low-energy neutrinos we're used to from the Sun or distant supernova, these carry enough punch to suggest they were born in the most violent corners of the universe. And yet, when researchers looked for the obvious culprits, black hole jets colliding galaxies or annihilating dark matter, they found nothing powerful enough in Perseus to explain them. Neutrinos this energetic usually come with a calling card, a visible source like a blazar's screaming jet or a star being shredded by a black hole. But Perseus's neutrinos arrive without any obvious home address, drifting into our detectors like whispers with no mouth to utter them. That's the first puzzle. If they're truly coming from the cluster, what's generating them without leaving a trace in other wavelengths? One possibility is hidden particle accelerators, structures too faint or exotic for our telescopes to spot. Imagine a cosmic factory tucked between galaxies, where magnetic fields or shockwaves fling protons to unbelievable speeds. When those protons collide with gas or light, they could spawn neutrinos as a byproduct. But why haven't we seen the gamma rays or X-rays that should accompany such events? Then there's the dark matter angle. If these ghostly particles are byproducts of dark matter annihilations or decays, Perseus, with its immense dark matter halo, would be the perfect place to look for them. The trouble is, the energy signature of these neutrinos doesn't match any known dark matter model. They're too energetic, too sparse, and too unevenly distributed. Some theorists suggest we might be seeing the fingerprints of a new kind of particle, one that interacts with dark matter in ways the standard model can't yet describe. It's a long shot, but in a universe full of surprises, why not? Perhaps the most tantalizing clue lies in timing. Some of these neutrinos arrive in small bursts, clustered within days or weeks, rather than the steady trickle we'd expect from a constant source. That implies something episodic, a process that flickers on and off, like a cosmic switch being flipped. Could there be hidden black holes in Perseus, too dim to see, belching out neutrinos in fits and starts? Or are we witnessing the aftermath of microscopic quantum black holes evaporating? A wild but not impossible idea. The implications stretch far beyond astrophysics. If these neutrinos stem from new physics particles or interactions outside our current understanding, they could be the first hints of a reality far richer than we've imagined. Every new detection peels back another layer of the mystery, teasing us with questions we're only beginning to articulate. For now, the ghost particles keep drifting in, silent and relentless, each one a postcard from the universe's most secretive corners. We know the universe is made of more than just the stars and galaxies we can see. Ordinary matter, the stuff of planets and people, plays a crucial role in the cosmic balance. But when astronomers tally up the expected normal matter, or baryons, in the Perseus Cluster, something doesn't add up. According to our best cosmological models, this colossal gathering of galaxies should contain a specific fraction of baryonic matter: protons, neutrons, and electrons relative to dark matter and dark energy. Yet when they measure what's actually there, the numbers come up short, not just by a little, but by a staggering margin, as if someone siphoned off nearly half the cluster's ordinary matter without leaving a trace. This isn't just an accounting error. The missing baryon problem plagues galaxy clusters across the universe, but Perseus stands out because of how well studied it is. We can map its galaxies, weigh its dark matter, and measure the scorching gas between its stars with incredible precision. And the more data we collect, the more glaring the gap becomes. The cluster's baryons should be visible in three main forms: the stars in galaxies, the hot plasma filling the space between them, and the cooler gas clouds drifting through the void. Yet even when we add up all these components, the total falls short. So where's the rest? One possibility is hiding in plain sight. Some baryons might exist as ultra-diffuse gas, too faint to detect with current telescopes. Imagine a fog so thin it's nearly invisible, spread across millions of light years. These wisps of matter could be lurking in the cluster's outskirts, their faint glow drowned out by brighter emissions from the core. Future observatories like the upcoming Athena X-ray telescope might finally spot them, but preliminary searches suggest this can't account for all the missing mass. There's simply too much unaccounted for. Then there's the intergalactic highway theory. Galaxy clusters like Perseus are connected by vast filaments of gas, part of the cosmic web that spans the universe. Some of the missing baryons might be tied up in these threads, too spread out to register in our surveys. But if that's the case, why doesn't the math balance out when we account for these structures? Simulations show these filaments should contain some extra matter, but not enough to close the gap entirely. The most radical explanation: the missing baryons might have been ejected entirely. Galaxy clusters grow by cannibalizing smaller groups, and during these violent mergers, shocks could fling normal matter clear of the cluster's gravitational grasp. Think of it like a cosmic sneeze gas gets blasted out at high speeds, escaping detection because it's now too diffuse or too cool to emit X-rays. There's some evidence for this in Perseus, with faint traces of gas stretching far beyond the cluster's visible boundaries. But again, the numbers don't quite add up. What makes this mystery so tantalizing is its universality. The missing baryons aren't unique to Perseus, they're a cosmic pattern, suggesting a flaw in our understanding of how matter assembles on the largest scales. If we can't even account for the ordinary stuff, what does that mean for our models of dark matter and dark energy, which rely on precise balances between all components? Perhaps the answer lies in something we've overlooked, an unknown phase of matter, or interactions between baryons and dark particles that subtly alter how we detect them. Until we solve it, the missing baryons remain one of astrophysics' most persistent puzzles, a quiet reminder that even the most familiar parts of the universe still hold secrets waiting to be uncovered. Among the countless galaxies swirling through the Perseus Cluster, some stand out not for their size or shape but for their unbearable restlessness. These aren't just active galaxies with supermassive black holes feeding at their cores, they're cosmic strobe lights flickering with wild, unpredictable brilliance. While most quasars and active galactic nuclei brighten and dim over months or years in relatively stable cycles, these celestial rebels flare and fade erratically, sometimes in mere hours, as if someone keeps flipping a cosmic switch at random. The speed of these changes isn't just unusual, it's downright impossible under our current understanding of how black holes feed. Picture a campfire that roars to life one moment, then shrinks to embers the next, only to explode again before you can blink. Now imagine that fire is a galactic core, millions of times the sun's mass, behaving just as erratically. That's the enigma astronomers face. The variability of these flickering AGNs defies the physics of accretion disks, the swirling rings of doomed matter that power active galaxies. According to Einstein's theories, these disks should have a minimum size dictated by a black hole's mass. Even for a modest supermassive black hole, that disk would span farther than our solar system, meaning changes in brightness should take weeks to ripple across its surface. Yet in Perseus, we're catching galaxies that double their luminosity in less time than it takes Earth to complete a single rotation. So what's causing this cosmic whiplash? One radical theory suggests these black holes might be snacking on stars instead of gas. When a star strays too close, tidal forces rip it apart in a spectacular flare-up called a TD tidal disruption event. But TDs are rare, and these galaxies flicker repeatedly like a faulty neon sign. Another idea proposes magnetic reconnection, twisted magnetic field lines near the black hole snapping and releasing energy in bursts. Yet even this can't fully explain the sheer speed of the changes observed. The most intriguing and controversial hypothesis: the flickering might come from something crossing our line of sight, not ordinary matter, but a dense swarm of orbiting objects. Imagine a cloud of planet-sized debris circling the black hole at relativistic speeds, casting shadows and magnifying light as it passes between us and the accretion disk. It's a cosmic puppet show with unseen actors manipulating the brightness we perceive. But here's where it gets even weirder. Some of these flickering galaxies show no signs of the extreme physics needed to explain their behavior. Their X-ray emissions, usually a dead giveaway for black hole activity, remain stable even as their visible light dances erratically. It's as if the engines powering these galaxies are decoupled, with one set of rules governing their light and another ruling their high-energy output. Could this mean we're seeing entirely new black hole accretion modes, or worse, that our models of space-time near these monsters are fundamentally flawed? The implications ripple far beyond Perseus. If black holes can flicker this fast, it challenges our basic assumptions about causality and scale near these gravitational beasts. Are we witnessing some quantum effect playing out on macroscopic scales? Or could this be evidence of black hole surfaces structures theoretical physicists have debated for decades, interacting with infalling matter in ways we've never imagined. Every flicker from these galaxies is a Morse code message from the edge of known physics, and we're only beginning to decipher what it means. One thing's certain: in a universe where even black holes refuse to follow the rules, the strangest discoveries might still be ahead of us. Among the wildest and most tantalizing theories to explain the Perseus Cluster's strangest behaviors lies an idea ripped straight from the cutting edge of theoretical physics: cosmic strings. These aren't the twine you'd find in a toolbox, but hypothetical cracks in spacetime itself, relics from the universe's birth, thinner than a proton yet denser than neutron stars, stretching across millions of light years like invisible wires threaded through the cosmos. If they exist, they'd warp reality around them, bending light, distorting time, and potentially sculpting the bizarre phenomena we're witnessing in Perseus. Imagine spacetime as a frozen lake, smooth and unbroken until the ice fractures. Cosmic strings would be those cracks, formed during the universe's rapid cooling just after the Big Bang, when the fundamental forces of nature split apart. Unlike black holes, which crush matter into singularities, strings are pure spacetime defects, infinitely long, unimaginably thin, and under such titanic tension that a single inch would weigh more than Mount Everest. Their gravitational pull wouldn't behave like ordinary matter. Instead, they'd create razor-thin kinks in gravity's fabric. A galaxy drifting near one might suddenly veer off course, its motion defying predictions. Gas clouds could be sheared in half, their particles accelerated to relativistic speeds without a visible culprit. Even light passing by would split into double images, as though the universe itself had developed a glitch. This could explain some of Perseus's most confounding quirks. Take those ultra-fast galaxies moving as if yanked by invisible ropes. Cosmic strings could be the ropes, their gravitational wake imparting impossible velocities. Or consider the cluster's oddly aligned galaxies. If strings thread through space like puppet strings, they might nudge celestial objects into eerie synchrony. Even the missing dark matter zones might make sense if strings are warping our measurements, their immense mass skewing gravitational lensing maps in ways we don't yet understand. The most provocative possibility: these strings might vibrate, like plucking a guitar string. Cosmic disturbances could send waves of energy racing along their length, releasing bursts of particles or gravity waves. If such a vibration passed through Perseus, it might account for those phantom X-ray flashes, transient energy spikes with no visible source. Even the cluster's bizarre magnetic fields could stem from strings, their extreme tension generating currents as they slice through plasma, like a knife through molten steel. Of course, cosmic strings remain unproven, lurking just beyond the edge of established physics. But their potential fingerprints, anomalous gravity waves, unexplained double images of distant quasars, or sudden particle accelerations, are exactly the kinds of oddities piling up in Perseus. For now, they're ghosts in the equations, possibilities waiting for a smoking gun. Yet if confirmed, they'd revolutionize our understanding of the universe's architecture, revealing a cosmos threaded with invisible strings, humming with the echoes of its own creation. The Perseus Cluster, with its catalogue of defiance, might just be the perfect place to start listening. From vanishing dark matter to ghostly radio halos, rogue black holes to cosmic strings that might thread the universe itself, the Perseus Cluster isn't just a collection of galaxies. It's a cosmic hall of mirrors, reflecting back at us everything we don't understand about the fabric of reality. These 25 mysteries aren't isolated oddities. They're interconnected puzzles, each one tugging at the edges of our knowledge like loose threads in a tapestry. Take the missing baryons. Where does half the cluster's ordinary matter hide? Then there's the sloshing gas, defying thermodynamics with its razor-sharp temperature divides, or the galaxies spinning in eerie unison like dancers in a ballet no one choreographed. Even time itself seems to warp here, with black hole echoes bouncing back years late and neutrino bursts arriving without a source. What ties all these phenomena together? A single, humbling truth: the universe operates on rules we've only glimpsed. For every law of physics we've written, the Perseus Cluster seems to scribble a footnote in invisible ink. Perhaps dark matter isn't just invisible, it might interact with itself in ways that sculpt entire galaxies. Maybe magnetic fields we can't yet measure are weaving cosmic order out of chaos. Or could it be that space-time itself is knotted here, tangled by relics from the Big Bang? The beauty of these mysteries isn't just in their strangeness, but in what they reveal about our place in the cosmos. We're not just observers, we're detectives piecing together a story where every answer leads to deeper questions. So what's your take? Could flickering galaxies hint at dimensions beyond our own? Might the phantom X-rays be echoes of collisions between parallel universes? Or is Perseus simply the universe's way of reminding us that curiosity is its own destination? The comment section is your launch pad. Share your wildest theories, your boldest guesses, or just your awe at how much remains to be discovered. Because the greatest lesson of the Perseus Cluster isn't in the answers we've found, but in the mysteries still waiting to pull us deeper into the dark.